me, it almost moves the model to something kind of in the like English department where essentially you use graduate students as low-paid faculty members. Yeah, pedagogy, Kyle. That's different than other similar words. Pedagogy is the science of teaching. Yeah, and you know that, again, for those of you who are in English philosophy or mathematics, I'm going to say a very politically incorrect thing, which is that the only reason they exist is because they've convinced the legislature that they're more important than they actually are. Moving on. All right, so yeah, that was recorded. Yeah, I'm operating off of the faith that everyone who watches this recording is going to be in the STEM fields. All right. Yeah, math is in the STEM as well, but there were a couple of interesting things that I came up with that I wanted to show you. First of all, remember on Friday, I was kind of wrestling with the idea that, well, in order to be able to set an Amax pattern for these leaves that would give us a maximum total canopy photosynthesis, we really have to have the slope of your PRI line, your initial slope be related to your Amax, and your dark respiration has to be related to your Amax. And what I found was that it wasn't actually that difficult to do. When I was plotting these against each other, they matched up pretty nicely with each other. So I just went ahead and did that. Now it's not going to be perfect, but it worked out pretty well. So now all of these are tied to this Amax here, and you can change your total Amax for the system and see what happens. And so that was actually pretty fun. So why not just ramp up your total maximum photosynthesis for your canopy as high as it can go, and won't that give you your highest maximum photosynthesis, particularly in a highlight environment? So I'm going to open with that philosophical question for all of you and get your thoughts. So if we just maximize the maximum photosynthetic rate of our leaves, well, let's say let's do 1,000. I mean, we're gonna maximize our leaf photosynthetic rate here. Let's see what happens when we maximize our total canopy photosynthetic rate. I mentioned this to the online students. I don't know if I mentioned to all of you. How many of you have used Solver before in Excel? Okay, one or two of you. So let me show you real quick how to use Solver. Solver shows up under the data tab here, or sometimes it does not show up under the data tab. If you go to the data tab and look on the far right side and Solver does not show up, you need to do the following. Go to File, go to Options, and it'll pop up to this. Don't be intimidated by all this stuff here. All you've got to do is go to Add-ins, and then at the very bottom where it has the Excel add-ins, go to Go. And if Solver is not showing up, it is because Solver is not checked in here. So if I click OK, you see Solver disappear here. If I go back to Options and Add-ins and go and turn on the Solver, then it's going to show back up. If you want to run statistics in Excel, this is also where you can add your analysis tool pack, which is all of your statistics in Excel. I highly recommend using the statistics tool pack in Excel as opposed to statistical software, because I'm sure Excel does everything exactly right without you really needing anything. I I'm being facetious there. Excel has some nice statistical functions, but it's designed around somebody who just needs to do kind of a quick and dirty analysis for most of their things. I wouldn't use it if you're getting ready to publish a journal article, just because it's limited in what it can do here. So now I'm going to go to the solver, and the cool thing is, what I can do is I can tell it, okay, I want to maximize my total net photosynthesis, which should be an AP2 right here. So right now this is a negative number. So my goal is to get it to be more positive until it can no longer be more positive. So I'm going to go here, I'm going to set this to a maximum, and then I'm going to change this first cell right here, which all of the other cells are linked to in some form or fashion. And what it should do is it does what we call an iterative function, meaning that it plugs in numbers, and as those numbers start to give us a better outcome, it plays around with those more and more and tries to give us the best outcome possible. Now, just be warned on this, and again, Dr. Kelly, I think, probably knows more about these theories than I do, but my understanding is, and from my experience, there are such things as local maximums. So if you put in a set of values that allow you to go to some peak value that is here, maybe you've got a bigger peak value over here, but once it starts getting better values on the left, it doesn't really start looking anywhere else for those values. So it is possible to get a local maximum in some cases, but for most of the stuff that we do, it works out pretty well. Just be aware of that if the values don't quite come out the way you expect them to, maybe you need to start with values that are a little bit closer to where you're trying to get. So I hit solve here, and now there are two possibilities. Either it's going to say, all right, it found a solution, everything looks good, we're happy, and if you keep the solver solution, whatever values have been changed are going to stay changed in the model here. Sometimes it will say that it did not find a solution. It'll give you a reason why. If it didn't find a solution, then it's kind of back to the drawing board. But in this case, I keep my solver solution, and my total PNet is AP. Oh, I have this set for an entire daily setup here. Let me change that to just this PNet here. I'll explain why in a minute. Let's see. So you can tell I've been playing around with this over the weekend so let me set that one to a maximum solution, and lo and behold, I've got a negative net photosynthesis going on for my solution here. So what is this plant doing? And I'll accept two answers. But if we have net photosynthesis going on, especially if it's going on over an entire day or an entire period of time, what's going on if we have net photosynthesis or negative net photosynthesis? Yeah, we've got net respiration, which is answer number one, which is correct. Good. That was, I think, the more logical answer to give. So great job, Ravi. Now, all of you have to come up with the more difficult answer. If we have net respiration occurring day after day, what do we have occurring? Okay, well, in this case, we've got lots of light, but aside from that, aside from the light environment, what did you say, Kyle? No growth. No growth, okay. Not only no growth, we actually have a plant that is shedding carbon like crazy. And what happens if a plant sheds carbon like crazy for a few days? Death. So in this case, we're at an unsustainable situation because essentially we're burning through more carbon than we're producing. Leah. The question was, so this is kind of what a seedling would look like early on before it starts having net positive photosynthetic rate. Yes, and that's part of the reason that that portion of a growth cycle is called heterotrophic growth, where that plant is essentially feeding off of the resources that were made available to it through the seed. So it's critically important for that plant to get up and to start getting net positive photosynthesis before those resources run out, because otherwise it dies. So great tie into that. So what's going on? We've got plenty of sunlight here. Why do we have negative P net? Because since respiration increases with our maximum net photosynthesis, we've got large quantities of dark respiration going on here, which become a major problem here. So let's bump this down to 100 here. And now you see, oh, that's crazy. Let's go ahead. Oh, that's because this number is greater than 100. Okay, let's go ahead and run this again and just kind of see what happens as we run this with a more logical maximum here. So what you see is you're producing two sets of leaves, or two areas of the canopy that have greater photosynthetic rate at a high light level. You've got one that's moderate light level adapted and one that's low light level adapted. No matter how you run this model, generally that's the pattern that you find in this case, is that the models that work the best have a combination of leaves that are adapted to high light levels and low light levels. So, you know, play around with this a little bit. Because of the model parameters that I have set, it's interestingly enough, your very top canopy of the leaves usually is not showing up as the one that is adapted to the highest light level. And I think it's constrained by the model I'm using, but it also makes sense as you look at most plant canopies. You know, most plant canopies don't just spread out a layer of leaves on the very top. You know, usually they're more triangular shaped, or, you know, non-flat downward triangle shape. Instead, they tend to kind of follow more of a spherical or ellipsoidal or triangular shape down to the bottom of the canopy, which makes sense because, you know, it allows you to have leaves that are more mature, that are absorbing more light and are causing greater photosynthetic capacity. Now, later in the season, that tends to not be the case. And I think partly because the leaves near the bottom of the canopy really shift into very low productivity mode. Can anyone think of some crops that really exaggerate the capture of the most sunlight at the very top of the canopy late in the season? What's that? Corn. So, grapevines? Very possible. I don't know much about grapevines. Do they produce a layer of large leaves at the very top of the canopy? Okay, so corn, grapes. Describe what is going on with corn here, and let me hand you the microphone because I'm going to do a terrible job of repeating it. So talk directly into the mic. So what do you see with corn?
I mean, first off, it grows so tall, but then, I mean, standard practice would be 30-inch spacing. So you've got canopy closure by middle of June. So you're thinking August, September, you've got no sunlight coming into the bottom parts of the canopy, and it's all being absorbed at the top.
All right, good. Does corn have a flag leaf?
Yes.
All right. That most of your cereal crops are going to have what's called a flag leaf. The very last leaf that is produced by the plant, and as a result, the very topmost leaf, is called a flag leaf. And it's the leaf that the stem comes out of that you're going to have the inflorescences on. And that leaf, if you look on a wheat plant, the flag leaf is probably twice as big as the next largest leaf on the plant. And very much the leaves on the plant at the bottom are the smallest. They get bigger and bigger and bigger. And then with the flag leaf, it's like this huge leaf that the job of that flag leaf is to capture carbohydrates so that they can be shuttled to the seeds and maximize the seed production. If you damage the flag leaf, whether it's by herbicide or insects, etc., you can see a noticeable decrease in yield through that damage. And so determinant crops very often, and even as Kyle mentioned, indeterminate crops to some extent are going to play the game of late in the season. They want to maximize the photosynthetic rate at the top of the canopy, and essentially they are already starting to partition nutrients and carbon out of the lower leaves at that time of the season. And that has two values. First of all, it gives it more time to put those resources into the fruit. And second, their respiration drops as that's being done. So they're actually maintaining their efficiency by doing it. So I found that interesting. So we're actually going to step into another interesting model today. And that is, as we mentioned on Friday and also a couple of weeks ago, there are, you can measure the amount of sunlight that a plant canopy is going to absorb based off of the leaf angle. Remember, if you've got completely flat leaves, they tend to absorb more sunlight. As they get more upright, they absorb less sunlight. And so if you graph leaf angle versus photosynthesis, you see something like this. So the K1 is going to be 0 degrees. The K2 is going to be, let's see, 25, then 50, then 75, then 90. And so what you see is at 25 degrees, you're not really changing your absorptance very much. At 50 degrees, you see a pretty noticeable difference in terms of the absorptance. What's the difference between absorptance and absorption? Absorptance is just a measure of the capability of a plant leaf to absorb, and absorption or absorbance is the quantity that's absorbed. So they're more or less the same thing. It's just absorptance is the capability to do so rather than the actual quantity that's absorbed. So here's 50 degrees. So you notice a significant difference, but there's still, as you get to higher leaf area indices, you know, kind of reaching the same general point. 75 degrees, you notice a significant drop off, and then 90 degrees, it's just 0 across the board. Now, this is assuming leaves that are pointing directly into the sun are infinitesimally thin, and essentially the sunlight is just missing them on both sides. Now, you know, I've never seen leaves that match those complete values or, you know, those complete circumstances, but as you approach the most vertical leaves, at some point, you're going to drop off towards 0 in terms of the absorption. So based on this, it would seem that plants with completely horizontal leaves are going to be the most advantageous, correct? Just based on this. Question here. Good question. The question was, you know, in a snapshot, this makes sense, but the sun's moving over the entire course of the earth every day. So, you know, wouldn't it make sense to have an array of leaves at different angles to potentially take advantage of that? I would say yes, and some plants seem to really play to that advantage. I wish I had a good video of it. We actually, when I was at Georgia, we did it with a high school student where we set up a camera and we were just taking pictures of the cotton canopy, you know, over the course of several days on about every 15-minute interval. And at the time, we didn't really have the software to be able to compile all of those pictures into a nice clean video. And you know, we really tried to control the light environment. That's kind of challenging to do. But one of the interesting things we did discover out of it was if you look at the cotton canopy or the cotton plants at nighttime, all of the leaves would go like this. And they essentially would drop down to facing toward the ground. And those of you who've been out in a cotton crop at nighttime, we're not going to talk about why people would be out in a cotton field at nighttime, but you very much notice that the leaves are facing down. As you first start to get the first rays of sunlight, an interesting thing happens, and it looks almost like the plants wake up and the leaves go like this, and they're ready to go. And early in the morning, you actually see the leaves kind of go like this. And throughout the course of the day, you see the leaves kind of adjusting like this to try to maximize their leaf angle in relationship to the sun. And like I said, I keep wanting one of these years to go back to that and get a nice high quality video of that so that I can show it in class. But we had like cases where like big rainstorm and windstorm came through and the plants going like this and leaves are flying off and the camera's running out of battery, and it was kind of wild and crazy. But very much plants try to adapt above and beyond the simple model. And so it's worth keeping that in mind. And I'm hoping to be able to at least give a snapshot of some of the variations that you can see in that as we're going. Yes, Vishnu. Hang on a second. This is going to be a good story. I want to make sure that we capture it for the online students here.
Sir, just I'm not clear about the leaf angle. In Nepal, just I saw most of the hybrid variety. They are high yielding. The leaf angle is like small, just like a compact stature, but the yield is very high. But if we talk about the open pollinated variety, the leaf angle is high. But I could not get this. Means leaf angle is lower for the hybrid variety, but yield is high. But if you talk open pollinated variety, leaf angle is high, but the yield is low.
Interesting. Okay, so just to make sure that I'm summarizing correctly, for some of your hybrids, you have a very upright leaf angle and the yields are really high. But for some of the open pollinated, the leaf angle is also high, but the yield is low, correct? Okay, interesting. So I would suspect it would be interesting to know in that case what the biomass accumulation is for the hybrids versus the open pollinated. And it would be interesting to see what else is contributing to the total yield in that case. But I think it's interesting that you bring up that, in some of these cases, having a very upright leaf actually results in a greater photosynthetic rate, even though if we're just looking at leaf absorption, it would seem that even at high leaf area indices, our total absorption is going to be decreased as we have more upright leaves compared to more horizontal leaves. Now, there's something else that researchers have gone into study, which is the Sunlit leaf area index. And so actually have a formula for the Sunlit leaf area index, which is simply the absorption divided by the cosine of the angle. And so the idea is that as you have more upright leaves, each individual leaf is going to absorb less light, but more leaves within the canopy and more area of leaves within the canopy is going to absorb sunlight. And so early in the season, I'm going to say at 0.5, here's what your canopy absorption looks like with leaf angle right here. You can see that it's dropping off in this case. And if you look at the average leaf net photosynthetic rate, it also drops off with leaf angle. So in this case, in a And this is a highlight environment. I've got it at 1500 micromoles per meter squared per second, which is, 3/4 of full sunlight on a sunny day. But you don't really have any advantage of having upright leaves in this case. Your average leaf net photosynthesis drops off over time. Therefore, if you look at your canopy net photosynthesis, it also drops off over time. And this just shows the sunlit leaf area index. So our sunlit leaf area index is increasing, but this increase in sunlit leaf area index is not enough to overcome the fact that we've got less absorption, and therefore our total photosynthetic rate is suffering. So early in the season, it seems to be a real disadvantage to have upright leaves. Now let's bump it up to maybe a leaf area index of 1, 1.5 and see what happens. So now you see this changes a little bit. Our sunlit leaf area index now, the curve is more upward sloping than it was before. And our total canopy net photosynthesis now is more or less even from leaf angle that's completely flat to leaf angle that is, more positive. So 40 degrees, that's a moderately upright leaf. That's almost 45 degrees at an angle to the plant here. So real quick, I just to throw this out here, since all of you are graduate students, I've got this online. I like having it online because it's kind of fun to play around with the numbers without having you recreate it. But I also realize that I'm giving away some of these opportunities to you to be able to come up with the numbers yourselves. How many of you would prefer like an assignment where you could create your own? Okay, well, you're going to be limited by the fact that you're trusting me for the math here.
So do we have a lot of programmers in here, or is it why the reluctance to try it out?
Right, why the reluctance to try it out? Yeah, yeah, that's putting a lot of trust in me. But maybe it goes back to the complaints that we got last week about me giving a take-home exam when everyone's trying to harvest their crops. I don't know. Speaking of which, if I get done 5 minutes early, I'll try to run through a few of the concepts on the exam, just because I think it's interesting to do. But let's see how far we get into this and see if at that point, if it's more interesting to keep talking about this or more interesting to talk about the exam. Let's bump this up now to a leaf area index of 4 and see what happens. Now, you'll notice that our canopy absorption, I guess in this case, is now more or less a flat line up to about 40, 45 degrees. At 60 degrees, it's dropping off some, but it's still at 85% of total canopy absorption for the horizontal. Our average leaf net photosynthesis is following the same pattern. Now look at our sunlit leaf area index and see how that's taking off on us. Now look what happens with our net photosynthesis. Our canopy net photosynthesis has actually risen above that which you would have with horizontal leaves by having leaves at a greater angle. So in this case, we're maximizing at about a leaf angle of about 60 degrees. So now we've suddenly gone from a situation where it's advantageous to have horizontal leaves to where it's actually advantageous for these plants to have vertical leaves. How many of you expected that to happen? Wow. It happens whether we expect it to or not. What is it they say? No one expects the Spanish Inquisition. Yeah, yeah. Monty Python says that. Yes.
So I'll be honest with you. I've never really calculated index for an actual living plant. I don't know what it looks like. What is a leaf area index?
A leaf area index of 10 is you walk out there and you are not going to see any gaps in the canopy, and you're probably going to see a lot of upright leaves. Let me put it this way. Imagine a cotton crop that you drive past in mid-August around West Texas, Lubbock. It's well irrigated and you've completely closed over the canopy to where you can't see any gaps down the canopies. That's a leaf area index usually of about 4. So imagine about doubling the number of leaves in that canopy, and that would be, you know, one of these greater leaf area indices here.
How does plants next to it and around it affect that? So like, let's say you have a single cotton plant out in the field, well irrigated, but it's one single plant. You have sunlight coming in from all different areas. There's no competition with competing leaves. How does that work?
Okay. And the question was, how does this work with a single plant versus with a community of plants? First of all, and again, I'll speak directly to cotton, which is relatively insensitive to space. It'll spread out when it's got the room. Any crop, when it doesn't have bordering plants with it, is going to yield greater relative to the individual plant. And so that's why you don't take measurements on the plants at the very end of a plot when you have a gap next to them. Or if you are doing that, don't do it anymore. But generally speaking, the leaf area index of that is also going to be difficult to calculate, because do you calculate it off of a 1 meter square area around that plant? Do you do it off of a 10 meter square area around that plant? Because really, that plant is in an environment where, you know, once you get the plants super far apart from each other, the plant doesn't really sense any other plants in the vicinity. And so the leaf area index, if you just go around the outline of that plant, the performance of that plant relative to leaf area index is going to be exceptional. But, you know, it's not really in an environment where that can be tested, because, you know, it's actually pulling resources from a much larger area than the outline of that plant. Is that a fair statement? So I would say this, if you look at wheat, for instance, if you plant wheat plants super close together, they're just going to have a single stem. If you plant them at a wider spacing, they're going to have 1 to 2 tillers on them. If you plant them at an even wider spacing, they're going to have 3 to 5 tillers on them. And so the plant structure actually changes, and it grows differently based on how much competition it has from within it. And so the goal is to plant it at a spacing that, with the resources available and the competition, that you maximize the total productivity of that system, as opposed to trying to maximize the productivity of the individual plants.
So for instance, we plant wheat in our cover crop is range for gold. They don't really want this.
Good question. The question was, you know, at our ranch, we plant wheat so the animals can feed off of the vegetation. So does it make sense for it to be spread out more? It kind of depends on what stages the plants are being eaten. And, you know, that's really going to be, you know, and how much water is available. It's not a hard and fast rule in terms of it's got to be at this density. But within an environment, you're going to find that some densities tend to be more productive than others. And, you know, depending on if the seed's cheap, you tend to want to shoot toward a little higher density, just because, you know, early in the plant growth cycle, when it's not competing directly with as many plants, it's going to put on vegetation more quickly. And if the animals are feeding off of it when it's at a relatively small stage, you know, you probably want it fairly close together just to maximize the growth potential of it. But there are cases when it would do better if it's more spread out as well. Boy, great questions. I feel almost like having graduate students is almost like having children, where, you know, questions or comments come up that show that people are really thinking about things and trying to figure out the world around them, which is a lot of fun. So let's try this really high leaf area index in this case and see what happens now. You'll notice that our canopy absorption up until about 70 degrees is more or less maximized. And our sunlit leaf area index also is increasing up to an asymptote. And therefore, our canopy net photosynthesis also has a point at which it's maximized here, substantially above where it was at the 0 leaf angle or these horizontal leaves. So with rice, which is a crop that grows very well in highlight environments, even though it's a C3 crop, it does very well in these high density situations because it's able to maximize the canopy net photosynthesis by having upright leaves in this case. So I'm sure what you've all been wondering is, what if we looked at net photosynthesis over an entire growing season, perhaps, where you've got both the early season and the later season, or low leaf area index and greater leaf area index, and actually see what the pattern is. So how would I do that if I was trying to do a whole bunch of iterations of this? Well, I'll tell you how I did it, and then you can decide how you would do it. I actually went in while I was in the administrative council meeting this morning, and I created a macro. And macros are really cool if you have to do something an awful lot of times, and if you can make sure that Excel doesn't do anything weird with your data. One warning, and I'm a big fan of using macros. This should look quite similar to what you're doing with your Arduinos. It's just a little bit different programming language. Yeah, probably. This looks plenty legible to me. I actually only added 2 things into this code. The rest of it was just click here, click there. But all this is doing is
yeah, we don't. So the Arduino, I guess one difference. This looks like this could be an object-oriented code.
right. That's a good point. Dr. Kelly mentioned one difference with the Arduino code is this appears to be an object-oriented code, and it is. This is actually just a lower. I say lower quality, but it's a lower functionality version of Visual Basic. But all it's doing here is it's saying, all right, copy a leaf area index, which I had, paste it into this spreadsheet that I just had, and then grab all the angle values for canopy net photosynthesis, copy them, transpose, paste them into a new sheet, and then let's pop in another leaf area index and try the same thing again. And I set up a do loop so that it just runs through all of the leaf area indices. But so I did all of that, and instead of it taking me like 2 or 3 hours to do all of this manually, I was able to just hit it and let it run, and it took like 3 or 4 minutes. But what it gave me was a net photosynthesis for all of these values. Isn't that cool? And then I set conditional formatting to where it changed the highest values to green and the lowest values to red. So what you can see is you've got this pattern of decreasing net photosynthesis by leaf angle at the lower leaf area indices. But then as you get to the higher leaf area indices, you see this pocket where it's dramatically improved in terms of the total net photosynthesis. Now I got thinking with that represents the total net photosynthesis pretty well, but it also, the one thing that it doesn't do is the relative net photosynthesis as related to horizontal leaves. So it's going to tend, I thought, to make it look like we're in better shape in this region and penalize everything in this region. Whereas, early in the season, yeah, it's great that late in the season or when you've got a big canopy, it's going to be, more efficacious, but early in the season, it's really working against you. So I decided to do the same thing, but just divide it by the horizontal leaves here. And what you see is that does change the pattern a little bit, but relatively quickly, you start to see these areas where having a greater leaf angle is not penalizing you as you get to even, low to moderate leaf area indices here. And then it also expands the leaf angles over which you're advantageous late in the season here. So I was pretty proud of that. I mean, and I also protected you from being assigned to be TAs at the same time. So I felt like it's been a very productive morning already.
So we've actually,
Yes.
sometimes when we use these devices, sensors, and they come with a really nice library, they allow us to set the sensor up as an object where we just change the properties of the object. So we do some similar type of object-oriented coding, but it hasn't been for every sensor.
Okay, interesting. So Dr. Kelly was mentioning that with the sensors that we're using, we can actually set some of the sensors up as objects to be able to do similar things with them to what we're doing with this coding, where essentially you can set it up to change things iteratively and essentially change them almost real time and changing the parameters. Interesting. So I'm now going to delete this from Blackboard, and if anyone wants to recreate this themselves. One thing I will warn you, when you open this up, you're going to see something at the top that asks, do you want to enable these macros? The risk with using anything that has fundamental programming that's hidden behind the software is that if I decided to, because when I was at the University of Georgia, when I was using spectrometers, we actually purchased an Excel program where the Visual Basic had actually been written as native Visual Basic code. And then they had it hidden with password protection on it. And it would actually control other programs on the computer. It would actually pull from libraries that were associated with the spectrometer and stuff. The thing is, and they've tried to put a lot of safeguards on these, but if somebody wanted to introduce malicious code, this is one of the ways that they could do it. So it's going to ask you, do you really want to enable this? In this case, I would say you're pretty safe because I didn't do anything that I could see as, causing problems to your computer. Mylea, you probably don't want to use this on your IG cast. I'm just kidding. Okay. Oh, nice. Okay, yeah. Yeah, clever. It's not going to surprise Robbie if students are going to him and saying that bad things are happening to their computers as a result of Dr. Ritchie. Yeah. Anyway, so what's the take home from this? The take home to me is that it's interesting that you can actually, in some cases, do something that fundamentally, when you're starting out with it, it appears that you're not favoring the plant by making a change to it. But, we've actually discovered that these plants adapted in these different ways can actually become more productive as a result, which I think is pretty cool. And it's a big reason that plants like rice have increased their yield, not only through an increased harvest index, but through an actual change in the leaf architecture. All right, shall we go through the exam? By the way, on this canopy photosynthesis, I've got a bunch of questions in here that are kind of interesting. I've actually kind of covered all of this through today's lecture, so don't expect me to strictly be going back to it. Oh, this goes back real quick to the question that Mylea brought up. What about your relative cosine of leaf angle over time? And this is, they're showing the K values of this crop canopy over a day. And you see that the K values actually change depending on the solar angle and the leaf angle. these are the equations that I used to get to the equation that we just did. Try them out if you want to. They're also in the Excel file. Same thing. Hey, looky there. At a leaf area index of 4.5, we see that same pattern that we were just talking about. But we got to see it in real time. So be familiar with Sunlit leaf area index, be familiar with the relationship between leaf angle and net photosynthesis based on photosynthetic photon flux. All right, let's see if I can find the exam and go through a few things really quickly with it. There are probably about 6 of you who don't see your exam scores yet because you emailed me the exam, and I haven't dug back through my email yet and graded those. Sorry, I will do that, I promise. In the meantime, I was pretty happy with the scores. Everyone seemed to do a pretty good job. Let's see. Let's do the face-to-face one. Let's see. All right, the first one, what is a thermograph? I got a lot of very technical answers for this, and that's good. No one really just said, oh yeah, this is just like a thermal image. Which, you know, and in the end, that's what they were doing, and they were just calling them thermal graphs rather than thermal images. Yeah. Okay. Anyone on answer B who said that the figure 1 diagram was better than Dr. Ritchie's class diagrams automatically got an F on me? I'm joking. But you did a pretty good job of saying what it demonstrated. The relationship of stomatal conductance with leaf area index, you did a pretty good job on it. This one I thought was interesting, on how do you test the effect of heat conductivity without the numbers being influenced by transpiration. Many of you gave some really interesting answers, like high humidity environments or stress the plant leaves to where they no longer have any conductance. You know, you're doing some pretty mean things to those plants. One of the things that I did not actually see very many people answer was the method that the authors used, which was they cut out pieces of paper in the shapes of the leaves, and then they actually did the testing with the pieces of paper. The idea being that pieces of paper aren't going to have stomatal conductance, but their other properties are going to be fairly similar. And so I found this question interesting just because the answer was there in the text, and I was interested to see who was just going to give me the answer there in the text. And most of you didn't, so I don't know if that's good or bad, but you came up with some very clever ways of doing this here. This one, describe why each material resulted in an increased or decreased temperature compared to the black reference. Almost all of these come down to a combination of what's the reflectivity of them and what is the emissivity of them based on their color. And so if you answered in that vein, you got all or most of the question correct. Everyone turn your head to the left. Okay, you can look back now. Describe why the leaf temperature shows a significant jump in temperature at the beginning of the light cycle, and why is the drop off slower than the increase at the beginning. So why do you anticipate that's the case? Why did we have a substantial jump? Let me see if I can pull that up real quick. I tell you, I think they could have done better. Let's see. Is this the one? Okay, yeah, yep. So why do we have this initial spike that's so clean, and then on the back end, it just kind of, you know, it drops off a little bit, but it's just still kind of trying to find its way here. This is probably the best example of that. Yeah. Yep. Now we'll never know. My thought process was on this, and I'll end it on this, was that the plant is favored more by responding quickly to an increase in temperature than it's necessarily penalized by responding to a decrease in light after the light's turned off. You know, losing a little bit more water at this point when you're in a low transpiration environment is not necessarily as big of a penalty as having your temperature spike and the whole plant dies. So you see the temperature spike and then immediately recover to keep from being damaged. And so the stomata open really fast when they need to. All right, everyone have a great rest of the morning and rest of the day. Stay safe if you're harvesting.